the birth rate, or birth-death transition probabilities, we're just going to use the combined probability mass function that you see down here at the bottom. So we know we're going to have a term for this, a term for the death rate, a term for nothing, and then the zero term for anything outside of that. And you can see that right here. Birth rate, if you increase by 1, death rate, if you decrease by 1, neither, if you don't increase or decrease, and then 0 in any other case. Okay, the continuous version, we're going to just make a few changes. Delta t this time represents a continuous time interval, so it is a real positive number. And we've talked about this before, if no time passes, then no transition is going to occur. The change in population is more useful to consider instead of the overall population size, especially if you're talking about large population, it can get sort of cumbersome. The Landau symbol, we're just going to keep it instead of calling it 0 for more accuracy, and the product Bn is used instead of B sub n. Okay? If you look up there at the top, I'm just sort of defining my notation. Delta x of t is the difference between the population size of those two different times. So we are looking at the probability that it goes from state I to I plus j in that little difference of time, delta t, and that equals the probability that the difference between the two equals j, the difference between the two at time delta t equals j, given that we already know at time t it was at state I. So just like before, we have the birth rate, and we're multiplying the population size, and then multiplying times the little amount of time passed. In the very, very simple cases, we just used delta t equal to 1 to make it very easy. Here I just left it as delta t. Same thing for the death rate. We have a difference. The second one is larger than the first, or sorry, smaller than the first, so that indicates a death. Here's our probability that neither one occurs, and then that is our rare or random occurrence of something outside of what we initially defined occurring. Okay, the derivation of the stochastic from the deterministic model. We want some way to link these two models together. We know that the stochastic models are just a series of birth and death rates. So I'm going to call the birth rates lambda n, I'm going to call all the death rates mu n, and the difference between those two, we're just going to set that equal to the differential equation form of the birth-death model, and we're going to see what conditions we can find that will satisfy this statement right here. All right, well, clearly, since the deterministic model is linear, then each of these terms have to be linear. We don't necessarily know that they just transition straight across, because since every time you run a stochastic model, you're going to get a different sample path, there is no guarantee that the birth rate here is exactly going to correspond to the birth rate here, or the death rate or the death rate. Okay, so here are my linear terms defined for the birth and death rates. Now I'm just going to subtract the two, do a little bit of rearrangement, and I find that if I let this equal b, this equal negative d, that is one possible solution that satisfies this equation. As long as you have something that whenever you combine all your terms together in the stochastic form, you come out with the same deterministic form, you know you have a valid working model. And as you can see, this is exactly what we had before for all the birth and death transition probabilities. Okay, now let's move on to the predator-prey model. This is the classic model that everybody who has ever done anything in biological modeling knows. The Lotka-Volterra assumptions are that in the absence of predators, the prey population will grow exponentially. Also, predators depend on prey for survival. all encounters between predator and prey are successful, and the population growth of the predator is proportional to the death rate of the prey. And I'll just sort of talk you through these equations. Okay, well, we know that in the absence of the predator, there was no interaction. That gives us exactly the same equation as what we had before. The simple birth model, it's an exponential, so we know that we're constructing it right. Let's see, the next assumption was, okay, predators depend entirely on prey for survival. That's this term right here. If there's no interaction, they're going to die off. Okay, the third assumption is that all encounters between predator and prey are successful. That's why we just have this law of mass action term there. It's just very straightforward. There's nothing else being adjusted or subtracted off. We're just keeping it very simple and the same. And the last one was that the rate of birth for the predator, the growth of the predator, is proportional to the death rate of the prey. That's why these two terms, this one here, this one up here, they look exactly the same. They both have a law of mass action going on. The only difference is the coefficient, because we cannot necessarily assume that those are going to be equal. Okay, the logistic growth model is essentially used to model a carrying capacity factor. The carrying capacity is simply saying, well, as the prey population increases, what percentage is left over for continual increase? So if you take the entire capacity of the habitat, subtract off the ones that are already there, divide by the overall capacity, you have the percentage left over. Since that's the percentage, we're going to just multiply it by what the first term was. So the birth rate times the percentage that we're allowed, and we're going to just subtract off the death rate like normal. It doesn't have any effect on the interaction, so this equation stays exactly the same. The refuge model, we are supposing that there is a certain amount of the population that can fit in the safe haven where every time the predator comes around to eat, then they can all hide in there, and there will be a certain number that will survive between every single predation. So instead of having just a straight law of mass action, we have the total number minus however many fit in the refuge. We're going to guarantee that every single time there is going to be that number in the refuge that is going to survive for the next time around. Since it affects the predation rate, it's going to affect this birth rate as well. So those are the only things that actually change. Okay, the derivation of the stochastic predator-prey from the simpler stochastic predator-prey, from the simpler stochastic model. Up here we had one species we were concerned with. So we had one birth, one death, probability of nothing, and then a rare or random occurrence. In this case, we have two species at work, so we're going to have 2 birth rates, 2 death rates, and we'll still have the big complement rule, and then the rare or random occurrence. So the birth is just dependent on the population size of the prey times the amount of time that passes. The birth rate of the predator depends on that law of mass action times the amount of time that passes. The death rate of the prey also depends on that law of mass action times the amount of time that passes. And the death rate of the predator, if there's no interaction, then we just get that. So it's really pretty straightforward and simple. You can sort of see where all the terms come from and everything. Okay. Now, this was one of the goals of this study, is to see if we could find a way to derive the stochastic predator-prey equations from the deterministic predator-prey equations. We're going to use the exact same technique as before. It was actually shown in Linda Allen's textbook on stochastic processes. In her book, it showed it for the competition model. So here I altered it a little bit to suit the predator-prey model, then the capacity factor model, and the refuge model. So just like before, up there at the top, I'm going to set the birth and death stochastic rates, the difference between the two, equal to the deterministic. Now, since we have two species at work, we're going to have to do two different derivations. We're going to have one for each equation in order to put all of it together at the end. So this is linear, but it has two variables. So that's how I get the birth rates and the death rates here. I'm going to do the exact same thing as before, subtract them, do rearrangement. This helps to meet the condition for A. This helps to meet the condition for minus B. And actually it comes out looking exactly the same as we expected it to look. For the predator population, go through the exact same thing, and we find that this will help to satisfy this coefficient here. This will help to satisfy the D coefficient at the bottom. Okay. Then if we put everything together, well, this looks very familiar. We saw this before. Birth rate of the prey, birth rate of the predator, death rate of the prey, death rate of the predator. The only difference is what we call the coefficients, but it is exactly the same model. Okay. The carrying capacity model, again, works the same way. The only difference is here we actually have three terms that we're looking at, and it is a quadratic equation. So we have to be sure, and whenever we go through and are doing our derivations for the prey equation, that we include a stochastic or a quadratic term in there. And these three conditions will help us to meet the requirements of that statement up there. Now, as you see, originally in the deterministic equation, you sort of think of the carrying capacity as being included with the birth rate. But here, we see that it can fall under the death rate. So that is just one small example of how you can use all different types of equivalents to go between the deterministic and the stochastic. There's not just one way to do it. You think of how many different ways you can get an even number on a six-sided fair die. There are three different ways to do it. So same thing here, this is just one of the ways. Let's see, this is the exact same as it was for the classic predator-prey model, so we're just going to leave these two terms the same, and this one is the big one that changes because we have the carrying capacity factor in there. Okay, the refuge model works the same way once again. In the top we have three factors again, or three terms. In the predator equation we have two. We can actually combine these because all of these are just constants as far as we're concerned. So we end up having only two terms in this. And see, we have the three terms in the top. And as you can see, the refuge part of it was put in the prey equation, it was put in with the death rate. But here, we can stick it in with the birth rate because it's actually guaranteeing that we have this amount every single time. So we can consider it as a birth rate in this case. For the predator equations, we actually moved this from the birth rate into the death rate. And you can see that that just pretty much follows directly like we were doing before.